So now I want to work through a few examples with the direct comparison test. Before I start working the examples, I want to talk about the way that I visualize direct comparison test in my head, because I think it'll help you to understand when can I make a conclusion about whether this series converges or diverges, and when is it inconclusive. Because just memorizing it in terms of ANs and BNs, and AN should be less than BN or whatever, can be... it feels like it's kind of impossible to retain the information if that's the way you're approaching it. So instead, if we have some kind of visualization, I think that'll help. So I'm going to try to keep this concise, but here's the way I'm picturing direct comparison test. First thing, you can only apply direct comparison test if the terms in your series are positive. So if I'm looking at the sum from, let's say, 1 to infinity, the terms are AN here, then AN needs to be greater than 0 for every positive integer n. So put positive integer n. Okay. Also, something else I want to have in my back pocket here for when we're ready for it. There's a theorem that was back in 9.1 that I actually left out in my class, but I know these videos are being shared a little bit, but 9.1, it was not mentioned in the notes that I released for 9.1. It says that every bounded monotonic sequence is convergent. Bounded monotonic sequence is convergent. That says convergent. Sorry. Okay, so we want to have that in the back pocket. Okay, what does this mean? So a sequence is bounded if there's a number that's bigger than every term in the sequence, and there's a number that's lower than every term in the sequence. So we've got we call it an upper bound for every term, and we've got a lower bound. And so let's say, I'm going to, for the sequence that I'm referring to, it's going to be the sequence of partial sums. So I'm going to give away that surprise. And I'll go ahead and label these as S1, S2, S3. So the sequence of partial sums is bounded if, like I said, some number that's below all of these terms, some number that's above all of them. Monotonic means it's monotone. So it's going only in one direction. You can have a function that's monotonically increasing or monotonically decreasing. It just means it never turns around. It never changes direction. So if it's bounded, and let's say it's monotonically increasing, I'm going to make an argument that the sequence of partial sums in this case must be monotonically increasing. Then, well, the only way both of those things can be true, there's an upper bound and it's always increasing. Only way that works is if it approaches approaches its upper bound like it approaches an asymptote. So it starts always doing kind of half of the distance that's left to that upper bound. It would have to look like that, which when a graph looks like that, so if it's approaching its like lowest upper bound, its lowest ceiling, if it's approaching that like an asymptote, then it's converging to some number. So that's the argument for that theorem. Now, I claimed that the sequence of partial sums is monotonically increasing. Let me make that argument. So S1, your first partial sum would just be the first term. S2, sum of the first two terms, so A1 plus A2. Now, if I'm assuming that every term is positive, then I've added something positive here. And so this must be greater than S1. S3, so S3 is the sum of the first three terms. Another way to look at that is it's the S2, it's the sum we left off on, plus the third term. And again, here I'm adding something positive. Sorry, Lego Masters is happening in the background. I don't have this area that I'm using is not closed off. But anyway, S2, and then I'm adding something positive to it, so this would have to be greater than S2. And then I'll do one more, so S4, as a shortcut for finding the sum of the first four terms, I could say, okay, well, it's the sum of the first three terms plus the fourth term, which again must be positive, so this must be greater than S3. So tying that together, what I've established is S2 is greater than S1, S3 is going to have to be bigger than that, S4 would be bigger than that, because we're always adding something positive. Now I'm going to add A5, which is positive, so S5 is bigger. Okay, and it would continue like that. So the sequence of partial sums is monotonically increasing. Each successive partial sum is going to be greater than the one that came before it, because you're adding something positive. So that means, back to this theorem, monotonic, we can check. That's automatically going to be true for the partial sums when we're looking at a series of positive terms. So the question is going to be just, is it bounded? That's going to be the issue. So that's the argument I'm going to make with direct comparison test is, can I show that it's bounded, or can I show it's unbounded? And that's what's going to be the deciding factor for whether the series converges or diverges, whether or not it's bounded. It's all going to hinge on that, since the monotone is a given if they're positive terms. Okay, so picture this kind of thing when you're thinking about direct comparison tests. Picture this right here, and I'll draw it. But okay, I'm 6 minutes in. Okay, let me see if I can get through these examples now and keep it close to 10 minutes. See if I can do it. Okay, so first series to consider here. So when we want to use direct comparison test, we choose a series that's quick and easy to tell whether it converges or diverges, and it looks a lot like what we're given. So notice if I just cover up the 5, 1 over 3 to the n, that's a geometric series. So that's what I want to compare to with series A here. Compare to the series 1 over 3 to the n, which is a convergent, I'm going to abbreviate here, convergent geometric series. Because the r is 1/3. Remember that a geometric series converges when r is less than 1. Okay, now the term-by-term comparison. We need to compare the terms in the actual given series with the terms in our comparison series. This one's got a bigger denominator, so you're dividing your pizza into bigger slices. I was actually just talking to my second grade son about this today, so while we're doing all the classwork at home. Sharing your pizza with more friends over here so you get a smaller slice. Okay. Anyway, couldn't help but bring it up. It was a big topic of conversation in our house today. Bigger denominator, smaller fraction. So, comparing to a geometric series, let me draw a little graph. So, picture your partial sums. The partial sums for this series, I'm going to plot in blue. I know that because it's a convergent series, so I know the sequence of partial sums is monotonically increasing. I know from geometric series tests that they have to converge to something. The limit exists, so this is going to approach some limit. So it is going to level off. The partial sums for this series will be bounded above. There's some ceiling that's below all the partial sums for this series since it converges. If there wasn't a ceiling on it, then it would just be increasing forever. There would be no number greater than all of the partial sums, which means it's increasing without bound, which means it diverges. Okay, not the case, since we know this is a convergent geometric series. So the blue dots here represent the partial sums for 1 over 3 to the n. Now, I don't want to use black because the contrast doesn't show up enough. I'll use blue for the partial sums for this series. So I know that when n equals 1, this is smaller, so the first partial sum is going to be smaller. When n equals 2, again, this is smaller, so I'm adding a smaller amount, then the second partial sum is going to be smaller. Okay, and so on. So if these are smaller terms, all the partial sums are going to be lower, but they are definitely monotonically increasing. So it's monotonically increasing. There's some ceiling above all the terms. Whatever the upper bound was for this convergent series, it's also going to be an upper bound for your smaller series. So, sorry, the kids are fighting. When you have a larger convergent series, the smaller series must also converge because you've got a ceiling on your partial sums for the larger series. That means you've got a ceiling on the partial sums for the smaller series. So larger convergent series forces the smaller series to converge. So we can say by direct comparison test, with the series 1 over 3 to the n, this series right here converges. It's important that you, when you say that a series converges, you say how you know. So what test, and if it's a comparison test, you have to also say what you compared it to. Those are critical pieces of information. It's not a complete answer if you don't give all of that information. Okay, so second one here. So I want to compare it to something that looks very similar to what I'm given. So in this case, I would suggest that you compare to 1 over 4 cube root of n. So I'm just taking away that minus 1. Now that's not exactly any particular type of series either, exactly. But if I put the 1/4 outside, which you can do, you can take out constant multiples like that, then I'm left with 1 over cube root of n, which the cube root of n I could write as n to the 1/3. And so now I know I'm looking at a p series. A p series with p equal to 1/3, which is less than 1. P series with p less than 1, that diverges. Okay, so I'm comparing it with the divergent p series, 1 over n to the 1/3. Or 1/4 times that. But I know I know for sure this series now diverges. Okay, now look at the term by term comparison we did before. So here's your given terms. Here's the comparison terms. Okay, now notice we're taking away one here. So I'm going to go back to the analogy I gave my 8-year-old son today. I'm sorry, but with fractions, sometimes we have to go back, way back to sharing pizza. Anyway, you're sharing pizza with fewer friends here, so you get a bigger slice. Bigger denominator, smaller fraction. This is the bigger denominator. Here you're taking away 1. That's a smaller denominator. So this is the... Did I say bigger denominator, bigger fraction? I hope I said smaller. I'm not going to go back and start over. But bigger denominator, smaller fraction. Or smaller denominator, bigger piece of the pie, if you want to look at it that way. Okay, anyway, the terms in our comparison series are smaller this time. So what does that say about our situation? So if this series diverges, I know the partial sums are monotonically increasing. It can't have an upper bound then. If it has an upper bound, it converges. So if I know it's divergent, it must just be increasing without bound. So here's your partial sums for 1 over 4 into the 1/3. Looks like that. It's just increasing without bound. Well, these terms are always bigger. So for n equals 1, the term in our given series, our first partial sum, is going to be bigger. And then I'm going to add something bigger than for n equals 2 over here. So you're going to get second partial sum is bigger. Third partial sum is bigger. So all of these partial sums for these terms is going to be bigger than the partial sums for these terms. So if you have a smaller divergent series, then you know that your lower sequence of partial sums is increasing without bound. That's going to push your larger terms, the partial sums anyway, for your larger terms is going to also have to go off to infinity. So when the smaller one diverges, that forces the larger one, pushes it up towards infinity as well. That's the way I picture it. So smaller divergent series forces the larger series to diverge. If you have a larger convergent series, that puts a lid on your partial sums. Now the lower one converges. Lower one diverges, bigger one diverges. Okay, so those are your two scenarios. So the conclusion then, based on all of this, is that this series diverges. Diverges. If I want to give a complete answer, by direct comparison test with the series 1 over 4 cube root of n. That would be a complete answer. You should also show your inequality and all of that, but even just to give an answer where you fully answer the question, you have to give all of that information. Okay. Last one. When am I up to? Oh, 14 minutes. Yikes. Okay. Last one over here. try to make this one quick. So 1 over 3 plus the cube root of n. What do we compare it to? One over the cube root of n. You probably guessed that. Oops. Which is a p-series, because that's equal to 1 over n to the 1/3. Which that's a p-series, p equals 1/3, which is less than 1, so it diverges. Okay, so we're comparing it to a divergent p-series. Now do your term by term comparison. So if I'm adding 3 in the denominator here, that's going to give me a smaller piece of the pie compared to this. So smaller terms here. Oof, this one diverges. That didn't quite work. Yeah, let me show you a picture. So now, bigger series diverges. So my partial sums for the 1 over n to the 1/3 are going off to infinity. Well, what does that say about the partial sums for the smaller series? If these terms are always smaller, if these terms are underneath, well, the answer is nothing, really. We can't reach a conclusion in this case. When the bigger series diverges, then the smaller series, it could converge, it could level off and approach some finite number, or it could also go off to infinity with the bigger one. We don't know. So this right here is actually inconclusive. Or at least the comparison that I chose in this case is inconclusive. So here's where you might switch over to limit comparison test, which is going to be the next topic in your notes, or rethink what you compare it to. So I have a feeling, because this looks so much like that p-series, which is divergent, I have a feeling that this diverges. But I want to compare it to something where this ends up, if I have a feeling this diverges, I want this to end up being the bigger. So I want to compare it to something that has a bigger denominator. What about comparing to n to the first here? So now, if I take the cube root of n, that's going to make this denominator smaller. And yeah, I know I'm adding 3, but plug in like n equals 1, n equals 2, n equals 3. Once you get beyond a certain point, this denominator is definitely going to be bigger than, like, take n equals 8. So here your denominator is 8. Here your denominator, cube root of 8 is 2, plus 3 is 5. So your bigger denominator is going to be over here. So these fractions are going to be smaller. And now, I know I need to wrap this up. This is the harmonic series. We know that this series, 1 over n, diverges. Let me get rid of, this didn't work out. So 1 over n, which diverges. So if I draw my graph one more time, I've got a smaller series that diverges. So the smaller series, the partial sums are increasing without bound. Then these terms are bigger, partial sums are all going to be bigger, so it must also increase without bound. So this comparison works. The first one didn't, but this one is actually conclusive. If we compare with 1 over n, so if we do DCT, that's why it's critical that you tell me what you're comparing to, because in some cases it works, some cases it doesn't. So direct comparison test with 1 over n, that does tell us for sure that this series diverges. And thank you for getting to minute 18, you guys who are still watching. Or minute 19, congratulations.